Good morning, class. Scores from yesterday's tests are in Zango. We spent about almost 6 weeks, about 5 weeks, on the series unit here. We're going to spend about another week on FRQs. So let's take a look at how you're asked to solve series FRQs on the AP exam. All right, so let's go ahead and start off taking a look at an example. So we're going to take a look at 2003 BC 6. Okay, so here's what's given. We are told that we actually have a rule to find the nth derivative. So our nth derivative at x equal 2 is the nth derivative at 2 is equal n plus 1 factorial divided by 3 to the n. And we know that to find so we're looking for a Taylor polynomial at c equals 2. And for part A, it's asking us to write the first 4 terms and the general term for that series of f at about x equals 2. So what we know is that our Taylor polynomial is f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared, and that's over 2 factorial plus f triple prime of 2 times x minus 2 cubed over 3 factorial, and so on and so forth. So we are told that this little formula right here is what's used to find the derivatives. We're also told, but this is only valid for n greater than or equal to 1. So they give us the fact that f of 2, which is the 0th derivative, is equal to 1. So all we need to do is find the first derivative, second derivative, third derivative, and substitute it in this formula. And then from that, see if we can figure out a general term. So our derivatives are as follows. So our first derivative, so that's when n is 1, the first derivative. So f prime of 2 is going to be 1 plus 1, so it'll be 2 factorial divided by 3 to the first power. F double prime of 2, so that's when the second derivative, so that's when n is 2, is going to be 2 plus 1 factorial, so it'll be 3 factorial divided by 3 to the second power. Third derivative, looks like that's going to be, well, that's when n is 3, 4 factorial divided by 3 to the third power, etc. So now substituting these derivatives into our Taylor polynomial here, so we have f of 2 is 1, so f of x is equal 1 plus f prime of 2 is going to be 2 factorial over 3 times x minus 2 plus, okay, f double prime of 2 is 3 factorial over 3 to the second, but remember we have this 2 factorial here, so that's going to be 2 factorial times 3 to the second, and then x minus 2 squared plus, now we need our third derivative at 2, so that's 4 factorial divided by 3 cubed, but again, we have this 3 factorial there, so that'll be 3 factorial times 3 cubed, and then times x minus 2 cubed. Now, what I notice here is that this 3 factorial over 2 factorial, well, this is 3 times 2 factorial. 4 factorial over 3 factorial, well, this is 4 times 3 factorial over 3 factorial. So it looks like the factorials in the denominator are all going to cancel out. So when we simplify, looks like we have f of x is 1 plus 2 over 3 times x minus 2 plus, so it looks like this is going to be 3 over 3 squared times x minus 2 squared plus, so again, this is 4 times 3 factorial. The 3 factorials are going to reduce, so that's 4 over 3 cubed times x minus 2 cubed plus. All right, so what's happening here? All right, so when n is equal to 0, when n is 1, when n is 2, when n is 3. Okay, so it looks like our numerator is, so when n is 3, I get a 4. When n is 2, we get a 3. When n is 1, we get a 2. So it looks like our numerator is n plus 1. So when n is 0, we get 0 plus 1 is 1. So that works. So plus, looks like we get an n plus 1. Okay, we're also going to get an x minus 2 to the n. In our denominator, we're going to get a 3. So this is 3 to the, when n is 1, 3 to the first, 3 to the second. So it looks like this is 3 to the n. So does that work? So n plus 1 over 3 to the n times x minus 2 to the n. So this would be our general term. Okay, so that's part A. Okay, now part B says find the radius of convergence for the Taylor series for f about x equal 2. Show the work that leads to your answer. Now that we have a general term, we should be able to find our radius of convergence. So our general term, so for part B, basically we have n is equal to 0 to infinity. So we get n plus 1 over 3 to the n times x minus 2 to the n. So we want to find our radius of convergence here. So we're going to use the ratio test. All right, so let's take the limit. As n goes to infinity, absolute value. So here we're going to get n plus, so a sub n plus 1 over a sub n. So we're going to get n plus 1 plus 1. So that's n plus 2 over n plus 1 times, so then this is x minus 2 to the n would be x minus 2 to the n plus 1 over x minus 2 to the n times, now because this 3 to the n is in the denominator, when we multiply by the reciprocal, we're going to get 3 to the n and the numerator over 3 to the n plus 1. Well, right away I see that the limit as n goes to infinity of n plus 2 over n plus 1, so the coefficients are the same here, degrees are the same, that's going to equal 1. 3 to the n plus 1 is 3 to the n times 3, so 3 to the n divided by 3 to the n, that'll leave us with 1 over 3. And then x minus 2 to the n plus 1 is x minus 2 to the n times x minus 2. So x minus 2 to the n divided by x minus 2 to the n is equal to 1 there. So this leaves us with the limit as n goes to infinity, absolute value. So we're going to get an x minus 2 times 1 over 3. And we know that has to be less than 1. So absolute value of x minus 2 over 3 less than 1. Multiply both sides by 3. We're going to get absolute value of x minus 2 is less than 3. So our radius of convergence is 3. Okay. All right, so now let's take a look at part C. So part C says, let g be a function satisfying g of 2 is equal to 3, and g prime of x is equal to f of x. And this is for all x. Okay, so this part right here is really key. Because what we're supposed to do here is write the first 4 terms of g of x and then write the general term. Okay. So I have g of 2 is 3, g prime of 2 is going to be f of 2, g double prime of 2 is going to be f prime. So if I take the derivative here, I take the derivative there. So g double prime of 2 is going to be f prime of 2. And g triple prime of 2 will be f double prime of 2. And our fourth derivative, not sure if we need that, will be f triple prime of 2. So these values we already know. Okay, so we know that f of 2 from before, our f of 2 is equal to 1. So g prime of 2 equals f of 2, that's equal to 1. G double prime of 2 is equal to f prime of 2, and f prime of 2 is equal to 2 over 3. 2 factorial over 3. To the first, f triple prime, g triple prime of 2 is f double prime of 2, and f double prime of 2 was 3 factorial over 3 squared. And although I don't think we need this last one, we can still write it. The fourth derivative at 2 is f triple prime of 2, and that was 4 factorial over 3 cubed. Okay, so g of x is going to be equal to, okay, so g of 2 is 3, plus g prime of 2, which is 1, times x minus 2, plus g double prime of 2, which is 2 over 3, or 2 factorial over 3, times 2 factorial times x minus 2 squared, plus, so our next term, so this is g of 2, g prime of 2, g double prime of 2, g triple prime of 2 will be 3 factorial over 3 squared times 3 factorial times x minus 2 to the third. And when we simplify this, let's see, this 2 factorial and that one goes away. This 3 factorial and that one goes away. So our first 4 terms is 3 plus x minus 2 plus 1 over 3 times x minus 2 squared plus 1 over 3 squared times x minus 2 cubed plus, okay, so now let's generate our general term. So this is when right, so it looks like our general term is going to be, so it looks like here if we think of this here, all right, so 1 over 3 squared, x minus 2 to the third. 1 over 3 to the first, x minus 2 squared. So this is x minus 2 to the first, so this would be 1 over 3 to the 0. So it looks like the exponent for the x minus 2 is 1 more than the exponent here. And then if we think of this, this is 0, 1, 0, 1, 2. If this is n, then this 3 would be 1 over 3 to the negative first, which would be 3. So it looks like our general term is going to be 1 over 3 to the n times x minus 2 to the n plus 1. And we would start this series at negative 1 to get all of our terms. Okay. All right, let's take a look at part D. So part D says, does the Taylor series for G, as defined in part C, converge at x equal negative 2? Give a reason for your answer. So we want to know, does the series for G converge at x equal negative 2? All right. Excuse me. We saw before that our radius of convergence for the series is x minus 2 is less than 3. So 3 is our radius of convergence. So that means that negative 3 is less than x minus 2 is less than 3. Add 2. So we're going to get negative 1 less than x less than 5. So that's our interval of convergence without testing any of the endpoints. But what I notice here is that this negative 2 falls outside of that. So this series does not converge. That's a geometric series that does not converge at negative 2 because negative 2 is outside of the radius of convergence. So the answer would be no, negative 2 outside the radius of convergence. So I will, I will see you guys tomorrow. We have 3 more FRQs to try. So they are a little challenging. Work together and do as many parts as you can. And again, I'll see you tomorrow.